Okay, so now let us begin with big omega notation. As we have already seen big O notation, you will find, I hope you will find understanding big omega easier. Now the difference between big O, which we have already seen, and big omega, which we are going to see now, is that in the earlier one, the big O, the equation was that f of n should be less than or equal to c into g of n. Here these things have changed places. Now c into g of n is here, so c into g of n should be less than or equal to f of n. If you look carefully into this graph, you will see now what is happening. C into g of n is lower bounding f of n. In O notations, big O notation, g of n was upper bounding. Now g of n is lower bounding. So there we were trying to say that okay, this function will not exceed this function. Like our function fn will not give a value greater than the other function gn. Here we are trying to say the reverse of it. We are trying to say that okay, now fn will never give a value lesser than c into g of n. So this is lower bounding. C into g of n is now lower bounding f of n. You can see the same concept reflected through this inequation. So let me try some examples. For example, first is we have fn is equal to 6n and gn is equal to 2n. What we need to prove? We need to prove that f of n is big omega of g of n. Now this is a symbol notation we will use for big omega, this, okay. So now let us try to prove this. What we have to prove? We have to prove that this one is less than this. Let's try for c is equal to 1. For c is equal to 1, at n is equal to 1, this one will be 6, this will be 2. At n is equal to 2, this will be 6 to 12, 2 to 4. And you can see for further values of n, you can try it for yourself. Put n is equal to 2, 3, 4, 5, 6, and you will find that for c is equal to 1, this will be less than this one. This will be less than this one, okay. So we can say that for the c is equal to 1, our equation is being satisfied. You can also try for n is equal to 0. This will become 0 and this will also become 0. But for all practical purposes, we tend to care less about this n is equal to 0 case. The reason is that n is equal to 0 means no input, 0 input. And the whole of this asymptotic analysis thing, we are calculating things in terms as a function of input size. And actually we are saying that the functions are showing their true colors, their upper bounding and lower bounding only after a value of n known as n naught. So that is why n is equal to 0 case, even though you can mathematically, obviously yes, you can consider that, but that is of very less, you can say, practical importance to us when doing asymptotic analysis. So that is why you may find me skipping this case very often. So n is equal to 1 is equal to 6. Okay, so we see that for c is equal to 1 by 2, this condition is satisfied. Let me take another example of c. Let's say c is equal to, let me say c is equal to 8. C is equal to 8. Let's say what happens at c is equal to 8. C is equal to 8, at n is equal to 0, they both become 0. But at n is equal to 1, here we have c into 2 into n. So at n is equal to 1, this will be 6, n is equal to 1. This will be 2 into 1, 2, 2 into 8. This will become 16. At n is equal to 2, 6, 2, 12. And here 2 into 2, 4, and 4 8, 32. So what we observe here, that this value, the value of fn is smaller and the value of gn is bigger, and it is getting bigger and bigger. So you can also try it for other values of n, and you will find that this is not getting satisfied even for n is equal to, look, okay, I want to tell you one more thing, that look, for n is equal to 0, you may say this is getting satisfied, fn and gn are equal, but after n is equal to 0, they are not equal. N is equal to 0, they are both at 0, but after that they are not equal. So there may be some fluctuations in your graph. For example, if you draw it like this, there are some fluctuations over here. You may see we have not taken this value as n naught, or we have not taken this value as n naught, or we have also not taken, we have taken this as n naught. Even though after this value, this value, this gn has got fn has got higher values for some values of n, and gn has got lower values for some value, and you can see this in a graph. No, this one is our fn, this is gn, this one is fn. No, this is fn and this one is our gn, but still this and this are not been taken as n naught, only this one is taken. The reason is that even though for some further values of n, here fn is giving higher value and gn is giving lower value, but then after another value of n, it is changing. The function of the behavior of functions are changing, but it is only after this value, the n naught, that the behavior of function is now not changing. Now fn is for all further values of n giving a value higher than c into g of n. So you have to be very careful if you if you take two functions and you want to find out which one is upper bounding which one, and you want to find the value of n naught, you have to be very careful, because these kind of fluctuations, this kinds of thing may happen. You have to find a value of n naught after which the function is showing behavior in such a way that fn is now always having a value higher than c into g of n. Okay. For such values of n naught, n like this one, where it is having a higher value for quite some time, but then it is showing a change. It has started to give a smaller value. This will not be taken as n naught, and this also will not be taken as n naught. Okay. So that similarly here in this in this example, at n is equal to 0, they are both giving same values. But after, you see, at other values of n, like n is equal to 1, n is equal to 2, n is equal to 3, this example at c is equal to 8 is not satisfying our inequation. So we will say that this is not satisfied at c is equal to 8. Okay. I have already told you that it will be satisfied for some values of c. The sum could be all. It is not a restriction that it must not be satisfied for all values of c. That is not the case. But it is allowed that for some values of c it may not be satisfied, that for example here you may not be able to satisfy it for c is equal to 8. And also I will not be considering n is equal to 0 very often. I have told you the reason. Now let me take another example. Another example, example 2. Okay, let me write it from here. Example 2, fn is equal to 5n and gn is equal to 2n into 8. So what I need to prove? I need to prove that 5n, 2n plus 8 into c is less than 5 of n. This is what I need to prove, right? So okay, let me try for c is equal to 1. Let me try for c is equal to 2. Let's see what happens at c is equal to 2. C is equal to, okay, c is equal to 1. Let me try for what happens if c is equal to 1. This is 2n plus 8. That is, for n is equal to 1, this is 2 plus 8, that is 10, and this is 5. So this we should here you should get greater value for fn, but this one is giving a greater value. Let's try for another value. Let's try for n is equal to, let's say 3. So 2 3s are 6, 6 plus 8 14, and 5 3s are 15. So now you see that at n is equal to 3, this is giving a value smaller than this one, yani this is now smaller than this. But n is equal to 1, this was bigger than this. Let's see what would have happened at n is equal to 2. At n is equal to 2, 2 to the 4, 4 plus 8, 12. This would have been 12 and this would have been 3 to the 10. So at n is equal to 2 also this would have been greater and this is smaller. But it is at n is equal to 3 that this is becoming lesser and this is becoming larger. So we can say that at c is equal to 1 our condition is satisfied. Okay. You can try another values of c. You have to prove this one greater. You can say c is equal to, let's say, 6. If we take c is equal to 6, let's say what happens for c is equal to 6, that will be 6 into 2n plus 8 and we have to prove. Now I am writing like this does not mean that this is true. I have to prove this. Right? Okay, let me not put this sign over here, else we will consider. This is what we have to prove. We have to prove that this is less than this. So at c is equal to 6 and n is equal to 1, this will 2 plus 8, 10, 10 into 6, 60 and 5 into 1, 5. Okay. At n is equal to 2, 4, 4 plus 8, 12 and 12 into 6, I think it is 72 and 2 into 5, this is 10. And you can try it for other values of n and you will see that this will not be satisfied for any value of n when c is equal to 6. Okay, even for n is equal to 0 in this case you will not be able to satisfy it because there is an 8 over here. I have another example. Okay. So I have one more example. This you can this is very similar to this and this. You can try this on your own, and if there is any problem with this, you may try to communicate with me. Now let me try this example. Okay. So having explained to you what is big omega, I now want to tell you what is small omega. Small omega. The small omega and big omega have a very similar relation, the kind of which we were having between small o and big O. Very similar, except that there we were talking about upper bounding, here we are talking about lower bounding. So Fn is said to be small omega of g of n when this equation will be satisfied for all values of c. Okay, let me write down the equation for you. 0 to c into g of n. Here we will not have equal. For all values of c greater than 0. For example, in this case where Fn is equal to n square and Gn is equal to n, Fn is equal to n square and Gn is equal to n, what we want to prove that n c into n is less than or equal to n square, and you will be able to prove this for all values of c. Okay, you take c is equal to, let's say, let me take c is equal to 1 by 3. So c is equal to 1 by 3 into n. Let us take n as, okay, let's start with n is equal to, let's say what happens at n is equal to 5. So 5 and this will be 5 square, 25. So this is obviously less than this, okay? Okay, not the equal to sign here. You may try for other values of c. Let's say c is equal to bigger values. Let me take c is equal to 10. Now at c is equal to 10, what will happen? 10 at n is equal to 1, 10 into 1, and here we will have 1 square. So this will be 10 and this will be 1. Now it is greater than this. Let's try for other values of n, like n is equal to, okay, let me take 4. So n is equal to 4, 10 into 4, 40, and 4 square is still less, 16. Let me try for n is equal to 8. N is equal to 8. What happens at n is equal to 8? 10 into 8, 80, and 8 square, 64, still less. N is equal to 10. 10 into 10, 100, and 100 square, 10 square, 100. And at n is equal to 11, at n is equal to 11, so 10 into 11, 110, and 11 square. Okay, so now we see that this is getting bigger. After n naught, the value of n naught in this case will be 10. This is getting the value of Fn is now getting bigger than the value of C into Gn. So C into Gn is lower bounding f of n after n is equal to 10. Before n is equal to 10, there may be some you can say changes or fluctuations in the behavior of your function. One more thing, and just as it was a case with your small o notation, similarly with our small omega notation, we can also write it, define n small omega like this. When limit n tends to infinity, f of n upon g of n gives a value of infinity, then we say f of n is small omega of g of n. In this case, we will say that f of n is small omega of g of n. Just to make a difference clear, in case of small o, this result should be 0. When the limit of f of n upon g of n is 0, we say that f of n is small o of g of n. When limit n tends to infinity, f of n upon g of n is infinity, we say that f of n is small omega of g of n. We may try it for this. Suppose limit n tends to infinity, we have n square by n. You can also call it like m limit n tends to infinity. This is n by 1. This obviously is equal to infinity. So in such cases, you may say that f of n is small omega of g of n. Now one more thing, amongst these two, that small omega and big omega, obviously it is the big omega which is comparatively more important and would be more frequently used. The reason is same, that because big omega has a capacity to represent tighter bounds, whereas small omega does not have the capacity to represent tighter bounds. For example, in this case, I could say that g of n is big omega of f of n is big omega of g of n, but I cannot say that f of n is small omega of g of n. So for the purpose of having a complete knowledge on the subject, it is better that you know about these things, but you should prefer using big O and big omega. And also one more thing, that whenever you calculate the run time of an algorithm, or you try using the tightest bound you could give, you can say that anything, like suppose if a function is like 6n cube, you can say it is lower bounded by something like n, or maybe lower bounded by something like under root n, but that is not a very tight value, very informative. So go for always whenever you are asked in exams, or whenever you are trying to solve things for your own practical purposes, try to go for the tighter value, for the tightest value. That will be in your best interest. Thank you.